thank you very much for coming today to the ViZn webinar. This is our 4th webinar of the year, and it's entitled, What is a Flow Battery and How Does It Work? We're very excited to have you here today. This will be a bit of a Flow Battery 101, and we hope to answer all of your questions as we go through the day. Just a reminder, like all previous webinars, the audience will be muted. In your GoToWebinar controls panel, there should be an area for you to ask questions. As John's presenting today, please ask questions. We will be holding a Q&A period at the end of the webinar. Additionally, we will be recording this event, so everybody who registered or everybody who is in attendance today will be receiving a link. You can share that link within your organization and share it out wide, please. Very fortunate today to be joined by John Lowell. John is the Chief Operating Officer of ViZn. He's responsible for all product configuration and manufacturing. He has 25 years of experience in a diversified array of industries, has held significant management positions on both technical, operational, engineering, and execution across a multitude of various technologies that are critical for high-tech, medical, consumer, and now energy. Very happy to have John with us today. Our agenda, we're going to do a couple slides of just ViZn introduction, setting the stage for our product, how it works, how it compares to the other energy storage options that are there for stationary applications. And then I'm going to hand it over for John, and he's going to take you through sort of Flow Battery 101, system basics, how the power stack works, how to contemplate and think about our chemistry compared to other chemistries that are out there. Our secret sauce, which I'll talk about, is our performance in terms of the ability to do long-duration energy and short-duration power services from a single platform for 20 years without degradation. And lastly, safety before we go into the Q&A period. For those of you who aren't familiar with ViZn's offering, what you're looking at here is an exploded view of our 4-hour solution. It's a 200 kilowatt 4-hour solution. We also sell similar systems in 20-foot shipping containers. The image in the right is about the size of a megawatt, and it takes up about the footprint of a tennis court. And you know, these systems, they last for 20 years. Like I said, they do both power and energy. As John will describe and as you will learn today, they can deliver power value streams, energy value streams for up to 20 years and really help your projects make the money that your end users are anticipating. One of the key differentiators that we hope to take away from today's presentation is this idea of power and energy versatility and the ability of the ViZn system to execute harsh, heavy-duty cycles with negligible power and capacity degradation over 20 years. Some of you might recognize the graphics from the bottom of this chart if you're shopping for lithium-ion batteries, because when you're building a lithium-ion battery system, early on, the architect and the engineering firm has to decide whether or not they're going to use long-duration lithium-ion battery packs or short-duration, higher power lithium-ion battery packs. And when you architect that system from day one, you need to determine whether or not it's going to be slated towards energy or slated towards power services for the 7 to 10 years you expect to use that system. And the ability to have the versatility to do both power and energy for 20 years is, you know, a key differentiator between ViZn and lithium-ion. John will talk about that today. You'll go into the science of why we can do that and how we do that. And we're looking forward to your questions on the topic. Before I hand it over to John, just a little bit on ViZn. ViZn is a 9-year-old company. We've been productizing our technology. We are now manufacturing ISO 9001 through our partnership with Jabil. We have had significant in-depth third-party validation and due diligence by both Black & Veatch and TUV Europe. We've been recognized by some of the leading energy storage independent agencies, and did exhaustive due diligence with Jabil prior to ramping up our ISO 9001 contract manufacturing. We've secured our first 80 megawatt hours in orders and commitments. We've done that through strong partnerships with companies like Schneider, Ryan, Alpha, and Hecate. All of our systems, when you think about a battery, it's basically a big DC block, right? And it's got to be integrated with controls, and it has to be integrated with power conversion systems. So when the complete turnkey system shows up on site, the battery can talk to the power conversion system, and it can talk to the controls, and you have limited to no system integration risk so that you can get from installation to revenue as fast as possible. And that's the core of our partnership with Schneider, and that flows over into our EPC relationships with Ryan and Alpha. And so, you know, a big part of our value proposition is to be able to turn to the end customer and say, here's how it works, here's how it's going to be executed. Here are our large partners, Jabil, Schneider, Ryan, Alpha, Hecate, who can bring you a complete turnkey system to be commissioned, you know, within months. With that, I'm going to hand it over to John Lowell. John, welcome. Take it away.
Hello, everyone. I'm John Lowell. I'm the COO here at ViZn, and I'll give you the walkthrough on flow batteries and the ViZn flow battery here today in the next 20-30 minutes. So just a quick basics on this ViZn flow battery. This is based off a 20-plus year design effort started off in actually research labs at Lockheed Martin in the 80s. And we have taken that and productized that. Scaled it up to full scale for utility use. It's packaged in basic shipping containers. That's for low cost as well as industrial environment survivability and ease of shipping. Our system's notable in that it is very simple manufacturing. It's based off of stamped steel, injection molded plastics. There's no complex chemical or plating operations or exotic materials that are required to build this battery. And that allows us both low cost and a relatively rapid scale up for manufacturing. The system is based around a robust battery stack, which we'll talk about a little bit here. That's really the heart of the ViZn system, the battery stack and its controls. We couple that up with essentially large tanks of chemistry that really give us our energy storage capability. We are using, unlike a lot of other batteries, a lot of other flow batteries, we're using an alkaline chemistry. It's relatively low cost. It's the lowest cost dollar per kilowatt hour chemistry that's out there on the market today. It's made out of common materials. It's really zinc and iron in salt or oxide forms that are very readily available. Nothing in our system, in our chemical side, really costs more than about $1 a pound or less. Now it's really battery stacks, tanks, electrolyte, and pumps to circulate it. That combined with our basic inherent design, it's non-toxic, non-flammable, and safe. It's made out of what are typically food-grade components. I'll go into that a little bit later and go into the details. But that's the overview of the ViZn battery. I'll go into the details on flow batteries here next. Next slide, Mike. Thank you. So here's flow battery basics. Everybody's familiar with a lead-acid battery in a car. Well, in a lead-acid battery in a car, the energy is stored in deposits on plates, anode plate and cathode plate. And they have very strict limitations based on physics, how much energy you can actually store plated up on a metal plate and then recover it. In a flow battery, what we're doing is we're actually storing the energy in the electrolytes themselves, in the tanks. And then that is essentially pumped through a reactor, which we call a battery stack. And essentially, the system's very simple. We pump an analyte material through the anode side, and the material reacts on the anode plate, and then it goes back into the same tank. Similar process on the cathode side. We pump the catholyte through the battery stack, reacts with the material on the cathode, and goes back into the same tank. We have a relatively simple cell design. Those cells are stacked together to make a stack. Our battery stack is 30 cells. It's roughly 3 foot by 3 foot by 3 foot. Weighs 900 to 1,000 pounds for a battery stack. We can get as much as 20 kilowatts out of one battery stack. The power in a flow battery, this is key difference between a solid state battery or most batteries. Power in ours comes from the number of cells in the stack, their area, and the number of stacks. And so that's how we get power as measured in kilowatts. The ability to deliver that power for an extended period of time is now independent of the plates, and it comes from the size of the tanks. So a flow battery allows the product designer to essentially optimize the system for the ratio of power to energy capacity. We have targeted our system to be in what is the sweet spot of the utility space, which is this 2 to 4 hour ratio of power in kilowatts to capacity in kilowatt hours. Key thing in flow battery stacks in any large battery array is cell balancing. Our system has built-in electronic controls which rebalances cells to each other real time while the system's running, and that minimizes the maintenance and also maximizes the stability of the capacity of the system, and you do not see the degrading that occurs in systems because of cell-to-cell imbalance. Other key thing in a flow battery is because our reactants are in the electrolyte and the anodes, cathodes themselves do not really participate in the reaction, we do not age the anode and the cathode. So the battery is not aged by charge and discharge duty cycle, and it's also, with all the electrolyte flowing through it, is cooled by the electrolyte itself. So these give you some very unique advantages in flow batteries. ViZn has over 80 patented claims, patented technology pieces in our current battery stack. We've been developing that battery stack based on the technology we extracted from the Lockheed R&D over the last 9 years, and we've got a relatively sophisticated battery stack and controls. Next slide, Mike. Okay. When you have the battery stacks, and that's the core of a flow battery technology, you have to package that up into a commercially viable, safe package that can be transported, installed, left in place, maintained and maintained for 20 years. What you're seeing here is the cutaway of our GS200 battery. This is a 200 kilowatt battery. Main components of this you can see is it's 2 stacked 40-foot shipping containers. And say our battery does not do small well. It was designed to be a utility scale system from the get-go. You can see the major components in that upper container. You've got 6 battery stacks on a sled and 2 sleds. So there's 12 battery stacks in this module. There's 4 pumps that are pumping out of tanks in the lower containers. So the system's quite simple. It just pumps electrolyte in a circle, pumps it in to the upper stacks. They return via gravity to the lower tanks, and they're pumped around again.
Hey,
key
John,
components in this. Yes, Mike.
Pardon me, John. I'm sorry. Several questions coming in on this slide about maintenance. And so how do you change out a pump? How often would a pump need to be changed? And how would one perform maintenance on the stacks?
Those are good questions. The system was specifically designed for maintenance. If you look at this diagram, you can see in the middle there's 4 little pillars with blue caps on them. Those are the pumps. Those can simply be lifted out and taken out the right end of the container as you're looking at it. The battery stacks that are in there, there is a service aisleway that can be walked along. All contactors, fuses, electronics boxes, wiring can all be accessed from inside the container by walking down the side. In the rare event that you have to remove and replace a stack, the stack is on a sliding rail and it can be essentially slid out the left end of that container and picked off that rail with a forklift and replaced the stack, and it slid back in. Everything else can be essentially accessed inside the container in the workspace and aisleway inside the container. Here's a little more detail on the stack. This is an exploded view of the ViZn stack. What you're seeing there is we really have electrodes with 30 cells. Each electrode is just nickel-plated stamped steel mounted in an injection molded polypropylene housing with some compression molded seals around it. Those are stacked up to make the battery stack. The chemistry that we run through the stack is a zinc oxide and a potassium hydroxide for our analyte, and an iron salt and potassium hydroxide for the catholyte. If the two are mixed, you do lose some performance, but there's no catastrophic reaction or event that occurs from mixing. We can cross-contaminate to relatively high levels with negligible impact on performance. We have proprietary additives in the chemistry that really get us our capacity and our life in the product. Key things in the system is controls. We do real-time balancing in the stack. The control package is a box on the side of it, not shown in this exploded picture. We have an integrated battery management system in every stack and then for the entire container. And then as a simple Modbus interface out to the real world for the plant level control packages and for interfacing with the inverter. Key piece of this are manifolding and housings. We do not have any valving or pumps to distribute material inside the stack. It's all done from the fluidics controls that are molded into the into the manifolds in the housings. Next slide, Mike.
As we're going to the next slide, John, I had a question come in that I think we might just want to address, and it was, how are the batteries charged?
Batteries are charged with the inverter. So this is hooked up to an inverter, and simply by varying the voltage field across the battery with the inverter, if you get the voltage up above the open circuit voltage on the system, it will begin to charge. And on our system, charging is accomplished by essentially plating zinc out of the analyte. So the zinc oxide circulating the analyte is converted to zinc, and it's grown up on the anode plate. And that is essentially how the system is charged. We can vary the voltage, varies the rate at which the battery charges.
Thanks, John. And we have another question coming in, and I think you might just want to address it as you're talking to slide 13. And it's in and around what type of personal protection equipment is required by people commissioning and servicing the battery.
That's a good leading question for the slide we're on here. The electrolyte that we have in the system, I'll just explain electrolyte for a moment and then explain the personal protective equipment. The electrolyte is made up of the catholyte is really yellow prussiate of soda. It's an iron salt dissolved in an alkaline solution of water, potassium hydroxide, and sodium hydroxide. The analyte is battery-grade zinc oxide dissolved in an alkaline solution of water, potassium hydroxide, sodium hydroxide. One of the key things on this system is none of the items there are toxic. The YPS is a food additive. We buy it in food grade. It's in gourmet sea salts as a decaking agent. It's in highway road salt as a decaking agent. So you can eat it. You can actually spread it on the roadways. Zinc oxide is a common ingredient in sunscreen, Desitin, baby powder, a lot of cosmetics. So the basic material there is non-toxic. So that gives us a lot of latitude in dealing with the electrolytes. They are caustic. They're strong basic solutions. Personal protective equipment is gloves, a face mask, and maybe boots. If you look up there, the National Fire Protective Code for our electrolytes is a 200. So 2 is a corrosive number, 0 is a fire, and the other 0 is a health hazard. So there's zero fire hazard, zero health hazard as ranked by National Fire Protective Code. This is equivalent to lemon juice or vinegar. In the quantity we're doing, they would have similar types of ratings. You can see the lithium ion is both hazardous in terms of reactive plus fire plus potentially toxic in terms of the electrolytes that are in lithium ion cells.
So John, I know this next slide is an eye chart, and we could probably spend all day on it, but I think it's actually worth taking a pause and having you explain what it is at 10,000 feet and explain why we picked the chemistry you just defined on the previous page.
Well, there's a lot of people out there that say there's, everybody's touting the next new late great battery technology is going to revolutionize energy storage. The reality of it is all the known electrochemical couples that you can build batteries out of have been known for many, many years. The chart that you see here, and you don't need to read it, it's not that important, but it is all the potential electrochemical couples that you can really make a battery out of. And where we're at there, you can see the little arrows, and this is the zinc iron salt battery that we make ours out of. The numbers on that are the electrochemical potential voltages. Key thing on this is anything in the red, you can make a very strong battery. As you move into the red, they become too reactive and too energetic to be safe. They will either spontaneously react and burn and explode, or they are reactive enough that you have to be very careful with them. Lithium starts to move into the red. Lithium is one of the highest energy potential batteries you get, which is great for cars, but not necessarily what you want when you have a facility the size of a Walmart. Our battery there is in the higher energy end of the safe range. And that combined with the aqueous electrolytes, it makes us non-flammable, non-explosive, makes us one of the safest batteries that are out there. So we are at there far enough to be energetic to get performance. We're safe because we're in the non-spontaneous, non-explosive area, and these are low-cost, readily available materials in the industry today.
John, as I go to the next slide, a question keeps popping up, and maybe we just put it to bed right here, and that is, how long will the electrolyte last before it needs to be changed?
Our design goal on our electrolyte is our electrolyte will last the life of the battery, which is 20 years. Now, that being said, is the electrolyte does have to be maintained. One of the reasons we do not have degrading in our battery over time is that we can actually get to and service the electrolyte. All electrolytes, reactive agents in batteries, age and decompose over time. In our system, we can service them, replace the lost water, replace the last reactive, rebalance state of charge, and completely restore the capacity and power of the system. So the electrolytes do not need to be replaced, but they do need to be serviced about once a year. In a heavy-duty application, it may be a little more frequent than once a year, but the electrolytes will last the length of the battery with annual servicing.
Thanks. Just jumping to this slide, which sort of looks at various popular chemistries out there and revisits the health comparisons, but talk to me about how these comparisons across various technologies impact projects from a siting, permitting, transportation, and end-of-life perspective.
Well, as materials become more and more reactive, you become more and more regulated. And we can look at some things. Lithium ion is one of the more reactive materials. It's not allowed to be transported. No batteries are allowed to be transported with voltages in any of the configurations of much over 60 volts. And lithium ion batteries have to be transported as modules and then assembled on the site into packs, because otherwise the voltages get too high. The same thing for a number of other batteries. The acidic batteries, particularly bromine, lead acid, those have heavy metal toxic components, and they are regulated for emissions, access to buildings, and that for both fire code and safety code locally. Vanadium is another flow battery. It's an acid-based flow battery similar to ours, but the vanadium is a known toxin and a carcinogen. And then the acid is concentrated sulfuric acid, which is both a fire hazard and a health hazard. So all those systems, because of that, have both transportation and installation problems. Our ViZn battery is actually transported dry. It is not transported with any electrolytes. The electrolytes are brought on site dry, mixed with water on the site. So the containers are both light, easy to transport, as well as non-hazardous material to transport. And that makes it much easier to do both the initial setup and the end-of-life recycling of the system.
Thanks, John. I'm going to go to the next slide, and it really talks about various flow batteries in terms of the alkaline or acidic nature of their chemistry, and then liquid-liquid versus liquid metal. And I think this is the key slide that talks to ViZn's unique capabilities in terms of providing both long-duration energy services as well as short-duration power services at a high round-trip efficiency. And I'll hand it back to you and walk us through it, please.
This will give a quick high-level contrast to different flow battery technologies. There's three basic commercially viable flow battery technologies that are out there today. One of them is vanadium. That's an acid-based liquid-to-liquid system. When I say liquid-to-liquid, means the energy is contained entirely in the electrolyte and there's no solid metal deposits in the system. Zinc bromine is another acid system. It also uses zinc. It's what's referred to as a hybrid or liquid metal battery. In one side, you plate zinc up, a metallic deposit on an anode plate. And on the other half, in the cathode part of the reaction, that is a liquid system. That is the same as the ViZn battery. Zinc bromine does that in acid. ViZn just does it in alkaline. Because we're an alkaline, we can't dissolve quite as much material. We have a little bit lower energy density, but we're much safer and much less corrosive. So those are the three basic flow battery technologies that are out there. When you contrast those, in the hybrid systems, you get one key advantage out of them. Because they actually plate up a metal deposit, that metal deposit tends to be porous, spongy. It dramatically increases the surface area and allows the liquid metal flow batteries, or the so-called hybrid flow batteries, to throw a lot more power than the liquid-to-liquid batteries. So they can produce a lot more power at a much higher efficiency number, and that gets you a real advantage to the liquid metal batteries. This contrast in the alkaline-based systems are lower cost. You can use plastics, you can use cheap, readily available materials. You don't have to use stainless steel. There's a lot of acid-resistant, corrosion-resistant materials. So they're lower cost. They tend to be safer. There's no toxic materials in the ViZn battery. Both vanadium and the bromine and the zinc bromine are toxic materials. And because they're can be built out of plastic and readily available materials, they tend to be less complex. So you have a lot more choices in alkaline for materials. We get away with essentially off-the-shelf, low-cost plastics, materials without going to exotic plated corrosion-resistant materials.
Thanks a lot, John. I'm going to go to the next slide, which really gets back into our battery and talks about, our, 10 times redundant approach towards ensuring, that the safest electrolyte out there is safe to deploy on site. So can you walk us through these systems?
Yeah. If you're going to do a commercially viable utility scale battery, you're talking about battery facilities the size of tennis courts or Walmarts. These are not small facilities, and they store a tremendous amount of energy. So they have to be inherently safe. And the ViZn system has a very safe chemistry, and it's also been designed for safety from the whole product and packaging. One of the key things, it ships dry and de-energized, so it's a non-hazardous material when it's on the road. There's no electrolyte in it, there's no chemistry in it, it's just plumbing, pumps, and electronics. The chemistry is inherently safe. It's food grade. Once neutralized, it's not even classified as a hazardous waste. And so the chemistry is both cheap and non-toxic. It's non-flammable. I mean, our system is actually our electrolytes are relatively effective fire suppressant. We do have a built-in fire suppression system, not for the electrolytes, but for the plastic and wiring that could be in the container, to make sure that any potential fire event or arcing event in the system is maintained inside the container. We have seamless tanks, so we're not fighting leak hazards, and those are backed up by a secondary containment diaphragm. So we have built-in secondary containment in the system to prevent any leaks. And then we have a wide array of safety sensors for leaks and problems in that are reported back through the battery management system and reported out to a remote monitoring site. Key thing about flow batteries, if you turn off the pumps, you turn off the energy. So we actually have emergency off. If you hit the emergency off button, the electrolyte drains into the tanks, and in 15 seconds, the entire system is de-energized. In case of earthquake, fire, plane crash, terrorist event, whatever, the system can be safely shut down, and it will not discharge energy under any situation. So, you know, these things give us inherently safe systems at large scale. And that is very critical for systems that are deployed at the edge of the grid in residential or urban, suburban areas where the benefit is best of having storage. Next slide, Mike.
Yeah, John, and as I go to this slide, before you address the recyclability and the end of use, I have a question that keeps popping up around the need for HVAC and whether or not you can deploy these in hot climates and what type of ambient temperature they need to be in.
Yeah, that's a key thing that I missed, Mike. Thanks for that, for the question. The ViZn system, the electrolytes are designed to run at around 45 to 50 C. They can go up as high as 55 C. That's 125, 130 Fahrenheit. The system likes to be warm. It's very good for that reason in hot climates, and it does not need any HVAC. We actually have to keep it warm to keep our heating losses to a minimum. The system will self-heat when it's running. And we can use this in the worst of conditions. We have looked at the most challenging conditions for solar applications in the Middle East. And you know, if they want to run in hot conditions with a very heavy duty cycle, at most we have to put a passive radiator on the system for nighttime cooling. We have so much thermal mass in the system, it can run for hours and hours at very hot conditions, and then you can dissipate the energy and cool the system down at night. Okay, talking to this system is really nearly 100% recyclable and reusable. The material in the system is really just steel, normal polypropylene plastics in terms of the cells and the plumbing, plus motors and some electronics. It can be stripped down and recycled with no really toxic residuals. The electrolyte, when neutralized, can be disposed of as a non-hazardous waste. Even with appropriate permits, it could even be disposed of in a sewer as industrial outflow. Also, there's no electrical hazards when the system's been shut off and drained of electrolytes. There's no residual electrical hazard, no heavy metals, no materials that have to be segregated or separated out for toxicity when the system is recycled at end of life. Final slide, Mike. Here, this is just doing a quick comparison to lithium ion. Lithium ion is the the battery system that's out there. It's been heavily developed for electric vehicles, and they're trying to move it into stationary storage. And while our battery is too big and too heavy to ever be in electric vehicles, lithium-ion is not necessarily the best material for stationary applications that need to be cycled once or twice a day. You know, we will have a 20-year life cycling the system multiple times a day at full depth of discharge and heavy-duty cycles. And we can do power and energy applications. We're non-toxic. We do not have any air conditioning loads, which makes us no cooling really required. So we're very well suited for hot climates. Lithium is particularly poorly suited for hot environments with heavy loads. It just really cannot do that. They'll overheat, and the batteries age very rapidly, and you're at significant risk of fire or failure. The system, you can access 100% state of charge. The system is not sensitive to being overcharged or over discharged. You do not damage the battery, even with significant overcharging or undercharging cycles. And the system actually is best suited if it's discharged completely once a day. That's actually good for the battery. It allows the control system to maintain balance better. You know, we can do the system, and this is typical of most flow batteries. They will do multiple duty cycles. They don't overheat. They are very good at getting rid of waste heat because of the flowing electrolytes, and heavy-duty duty cycles do not damage them by overheating. And then there's the low raw material cost. The electrolytes in particular are the cheapest electrolytes really out there today on a $1 per kilowatt basis, or kilowatt hour basis for the electrolyte itself. And end of life, the stuff can be simply recycled with little to no cost of disposal. So that's the quick overview compared to lithium ion.
Hey, John, I told you it wasn't going to. Yeah, I told you it wasn't going to be that bad. I've received a lot of great questions. I plan to go through the top 5 or 6 of them right now. I'll answer some. John will answer some. I'm receiving a lot of project-specific questions, and if you have a specific project that you're looking at, please send me an email at the email listed on the screen. We have a great applications engineering team. We can very quickly work with you to pick the optimum size of the battery and pair it with whichever existing generation or future generation sources you're contemplating for the site. We can run complete economics based on your load data, whether you're on-grid, off-grid, front of the meter, behind the meter, diesel hybrid, solar, wind, what have you. And we can help you build a 20-year cash flow pro forma and get the unlevered IRR with first cost and O&M costs all built in. We do that 3 or 4 times a week for our partners and for our clients, and it's a service that we provide complimentary, free of charge. Jumping into the question, John, we knew this was coming. Round trip efficiency, DC round trip efficiency, AC round trip efficiency. How does that vary across states of charge and power levels?
Well, that's a pretty complicated question. I'll see if I can hit it simply to, and if people got more detail, we can get into that later with more engineering documentation. Our round trip efficiency, DC to DC, which is DC power out divided by DC power in, is about 90% for our system when run at what we call nominal, which is roughly 1/3 of our max rated power. We're about 80% round trip efficiency DC when it's run at maximum power. Those are pretty good. One looks at coulombic efficiency as a battery measurement. That is really 99% or better, but the key thing that counts is the energy efficiency. Round trip efficiency from AC to AC, and this is including all parasitic loads, transformer losses, inverter losses, depends on the installation, depends on the equipment there. That's in the 72-74% range on our systems. Maybe as low as 70 to 72% at max power, but it's in the, roughly around the low 70s, which is pretty comparable to other systems when you include other parasitics for HVAC and other losses.
Thanks. The next one I'll take, and it asks about Black & Veatch. We talked about Black & Veatch and the work they've done, but specifically, what did they do and what did it result in? So Black & Veatch spent about 4 months with a team of engineers and PhDs crawling all over our factory, our engineering, our field data, and our manufacturing processes and quality processes at Jabil. In the second quarter, early second quarter of this year, they wrote a big 60 to 75 page report that will put you to sleep. It basically says that the battery works, the battery will last as long as we say it will, and our manufacturing and operations team are doing a good job and doing what they say they're going to do. If anybody's interested, please contact me at the email on the bottom. Happy to sign an NDA and provide you the full report, but I also have a 3-page PowerPoint summary I can provide you without an NDA. So welcome and happy to do that. I'd be lying if I said there weren't 15 questions in here around cost and price, and I'll respond to these. So, you know, the bottom line is that, you know, there's a lot of noise out there in the market in terms of battery manufacturers advertising what their prices are and what their prices are going to be in 5 years and what their prices could be if you submit a purchase order for, you know, 1 million units. And, you know, the fact of the matter is that depending upon the battery technology, if it's lithium ion, it makes up between 20 and 30% of the overall turnkey system cost, the first cost. But if you look at flow batteries, it ranges from 40 to 75% of the overall turnkey system cost. It's also critical to take into account operations and maintenance expense for things like massive change-outs of lithium-ion cells that could definitely have to happen between years 7 and years 15 in a project, and other operational expenses such as auxiliary loads and large HVAC loads that come up in various climates. And so what we do and what we can commit to is that the market is telling us and our customers are telling us that on a first cost basis, meaning the all-in turnkey cost of the battery, the power conversion system, the controls, the fence, the site work, the pads, you know, the security system, the barking dog if you need one, we come in within 5 to 10% higher or lower versus a comparable lithium-ion system. So super competitive on first cost, and then you got to layer in your IRR calculations, you know, roughly 2 times the life, double the duty cycle with negligible degradation. And what you get to there is a pretty robust side-by-side calculation from an unlevered IRR perspective.
I'd say, Mike, could I add to that just a second with a comment? One of the key things we look at the cost is the cost per kilowatt hour transacted. Because of the high depth of discharge and the ability to do heavy duty cycles, the cost per kilowatt hour transacted in our system is significantly less than other systems.
Thanks, John. Last question here, because I'm doing my best to sort through all of these and happy to talk about projects offline at the email cited. Lots of questions here around frequency regulation and high power services and fast switching, right? So we've talked about how we deliver high power, right? But there seems to be some confusion in terms of how we achieve switching. Do we have to reverse the flow of the pumps, or is that handled by the power conversion system and the controls? John?
Well, good question. There's no reversal of the flow on our system. It's always being pumped, always in the same direction. The only thing you have to reverse to go from charge to discharge is the voltage field produced by the inverter, and we can switch as fast as the inverter can switch. We have tested our stuff in full scale, switching as quickly as 8 milliseconds from full power charge to full power discharge, and again, that is limited by the inverters, not by the battery. In the real world, value is really controlling a lot of it in the control system and how quickly the controls react and what's the latencies in the controls. But the battery can switch as fast as the inverter can switch the voltage field.
All right. All right. I think we're going to wrap it up. And John, I want to thank you and everybody on the phone and everybody in attendance. I want to thank you as well. We will be sending out a link to the video. You have my email, which is right there on the final screen. I'm happy to reply to any questions you have and work through any projects you want us to price or quote or evaluate. So again, thank you very much and have a wonderful weekend.